For this lecture, we're going to talk about image enhancement. So with an image histogram, it measures frequency or how often something occurs. It can be represented by the function h of x equals q, where x is an intensity from 0 to 255 for 8-bit images, and this tells us that we see the intensity value of x for a total of q times. In other words, each input value x represents a digital number, and q is the frequency with which you see that digital number in your image. Let's take a look at what that looks like. So on the left, we have a man with a camera, and on the right is the histogram that corresponds with this image. If you look at the x-axis, these are digital numbers. The y-axis is frequency. There are approximately 1,500 pixels with a gray level of around 10. So if you find 10 on the x-axis, you can see that there's a corresponding value on the y-axis of approximately 1,500. And if you find the value of 170 on the x-axis, you can see there are approximately 1,200 pixels on the y-axis. This curve is not normally distributed, and it does have a concentration down in the lower values and then another concentration up in the range of 150 to 180, and this is a bimodal distribution. So how do we interpret histograms? If the histogram has too many values towards the left, then the image is too dark. If the histogram has too many values towards the right, the image is too bright. If the histogram has values that are concentrated or bunched up in the middle, the image will look washed out. If an image has bad contrast, we try to correct that by doing histogram equalizations. We try to make the image's histogram as flat as possible for good contrast. In other words, we're stretching it out. So if you think about probability, if you divide each histogram entry by the total number of entries, this will give you a probability density function. Histogram equalization seeks to modify the PDF so that all possible events are equally likely to occur. So here is a pictorial representation of that concept. So to review, an image histogram is a graphical plot displaying input pixel values on the x-axis, and in GIS this is referred to sometimes as a bin, versus the number or relative number of pixels for any given bin value on the y-axis. These histograms correspond with the images that are directly above them, so histogram B goes with image A, etc. If you look at the normal contrast image, you can see that the histogram is very close to a normal distribution. There is a peak at the 255 levels, which are the very bright areas in the image. If you look at histogram D, we see a low contrast and we see a bunching of the pixels in the center of the histogram. And if you look at the image in C, you can see that it's very grayed out and muddled. And then finally, with E image, we have the corresponding histogram in F. It's showing a high contrast, and there are sharp black and white values. Each bin in a grayscale histogram depicts a subgroup of pixels in the image, and they're sorted by gray level. The numeric range of input values or bins on the x-axis usually corresponds to the bit depth of the captured image. So for 8-bit images, it's 0 to 255. For 10-bit images, it's 0 to 1023. And for 12-bit images, it's 0 to 4095. We can see here examples of 3 original images: text on a page, a cat, and a plane landing with a speed limit sign in the foreground. And if you look at the images from 8-bit plane down to 1-bit plane, you can see the degradation of the quality of the image with increased blurring and decreased sharpness or resolution of the image. So, mathematical operations may be performed on the histogram itself to alter the relative distribution of bins at any gray level. When we manipulate a histogram, we can correct poor contrast and brightness to dramatically improve the quality of digital images. So, comparing these images of Einstein, the one on the left has more shadow and is darker, and then on the right, if you focus on his right cheek and right ear, you can see more details, for example. So this is the result of manipulating your histogram on the image. Here's an example of adding 50 to each pixel value, and it produces this result. And so if you look at the histogram on the left, the old histogram does have its values beginning at 0, but the one on the right begins at 50. And so by doing a mathematical operation and adding 50 to each value, what you're doing is you are lightening up or you're brightening up the image that you see on the right. With histogram stretching, this involves modifying the brightness or intensity values of pixels in an image according to a mapping function that specifies an output pixel brightness value for each input pixel brightness value. Here's another representation of histogram stretching. So we have another image here shown in A and B. In the top, there's a low contrast and a concentration of the images in the center of the values. When we stretch that out, we get a normal contrast, and we're making use of all of the integer values between 0 and 255 that the monitor can display. If image data were floating point values that ranged from negative 1.0 to positive 1.0, the image might be stretched such that data values of negative 1.0 are assigned a brightness value of 0, and then data with positive values of 1.0 are assigned a brightness value of 255 with a range in between. A linear stretch is used so that data values maintain the same relationship to each other as the original data. So in other words, the relative distance between two stretched values is the same as the relative distance between the two original data values. I know the numbers are blurred out in this image, and it's not important to look at the specific numbers here. It is the relationship and the concept, again, that with a linear stretch, you're maintaining the same relationship to the data. It is just changing proportionately because of the stretch. There are other types of stretch, such as Gaussian, equalization, or square root functions, and these use different models to assign those intermediate values between 0 and 255. So here's some details on a Gaussian stretch. It fits an observed histogram to a normal Gaussian form. The normal distribution gives probability of observing a value if the mean and standard deviation are known. So for example, you can assume number of pixels is 262,144. Number of quantization levels is 16. Then target number of pixels in each class for a normal distribution is the probability times 262,144. The cumulative number of pixels at each level is calculated, and the output pixel value is determined. Once a value of a column is determined, it is written to a lookup table. So here's the result of a Gaussian stretch. You can see that the curve, the black line, is representing the process of the Gaussian stretch. So, calculating a histogram equalization with a lookup table. It is done by calculating a target, the number of pixels to be placed in each histogram class. So the total number of pixels, image pixels over 256 equals n. The histogram of input image is converted to cumulative form with the number of pixels in the classes 0 to j represented by c sub j. C represents the cumulation. The histogram classes are labeled 0 to 255. And you can see the equation here. C sub j is n0 plus n1, etc., all the way up to nj for the total number of pixels. The output level for class J is simply C sub j over n, or the number of pixels in the target. This creates a lookup table for ease of computation. Here's an example of a lookup table that corresponds to the histogram equalization stretch on the left. So the value, or the cumulative number, of 132,385 divided by the total number of pixels gives approximately 8 if you look at the table 5.2. And it gives a very specific value of 8.1, and that's been rounded off to 8. So that would be your new lookup table value. With density slicing, the digital numbers along the x-axis of an image histogram are divided into a series of analyst-specified intervals or slices. So the digital numbers that fall within a given interval in the input image are then displayed at a single digital number in the output image. If 6 different slices are established, the output image will only contain 6 different gray levels. So if you look at the image on the right here, there are 6 levels of white, gray, and black, and that's because there were 6 different slices established. With density slicing, the mapping of a range of continuous gray levels of the single band to a single level and color is performed. Each range of levels is called a slice, and the range of 0 to 255 normally converted to several slices. This is effective for highlighting different but homogeneous areas within an image, and you do have the expense of you have a loss of detail. So even if the slice and boundaries colors are carefully chosen, you are going to lose detail. However, random color selections may say more about the psychology of the perpetrator than about the information in the image, and may confuse rather than enlighten. So I put this quote in here to keep your eye on, and remember that there is bias. And as an analyst, you are making choices and decisions about what to do with the data. Here's a density slice for surface temperature visualization. So on the left are digital numbers representing a value of temperatures from 28 degrees to 32.5 degrees Celsius. And after density slice manipulation, you can see that the colors are represented by, the colors are representing temperatures in the image on the right. So the warmer areas are shown in red and white, and the cooler areas are shown in blues. We're going to move on to filters. So what is filtering? It's a process. The process of filtering is also known as convolving a mask with an image. And this process is the same convolution of convolutions. So filter masks are also known as convolution masks. How is it done? The general process involves moving the filter mask from point to point in the image, and that at each point or pixel with an XY location value of the original image, the response of a filter is calculated by a predetermined relationship. All the filter values are predefined and are a standard. There's 2 types of filters, linear filters or smoothing filters, and there are frequency domain filters. So why are filters used? They're applied on an image for multiple purposes. They're used for blurring and noise reduction, and they're also used for edge detection and sharpness. With blurring and noise reduction, blurring is used in pre-processing steps, such as removal of small details from an image prior to large object extraction. Masks are used for blurring. There are 2 types, box filter and weighted average filter. So in the process of blurring, we reduce the edge content in an image and try to make the transitions between different pixel intensities as smooth as possible. So noise reduction is also possible with the help of blurring. So what are edges and filters? When we have sudden changes of discontinuities in an image, these are called edges. Significant transitions in an image are also called edges. And a picture with edges is shown below, or in this slide. So with edge detection and sharpness, we're taking the original picture in the top square, and then we are applying edges with the use of a filter to tease out the edge detection, and you can see that there is an increased sharpness in the image. So the edges there are showing as the bright areas. I encourage you to follow the directions in your syllabus and review spatial filters. There are iGet tutorials that are assigned for this lecture, and you can find the links here for part 1, part 2, and part 3. Please watch all 3 tutorials. Moving on to spatial convolution kernels, the most powerful image processing tools utilize multi-pixel operations, and this is where an integer value of each output pixel is altered by contributions from a number of adjoining input pixel values. So you have your pre-image on the left, you have a convolution performed in the middle, and then you have a post-image on the right. It can be mathematically represented as 2 ways. G of xy equals h of xy times f of xy. And this can be explained as the mask convolved with an image. Number 2 is just a different representation of different processes. So g of xy equals f of xy times h of xy. And this can be explained as an image convolved with a mask. So there are 2 ways to represent this, because the convolution operator, represented by the star here, which is a multiplication symbol, is commutative. The function h of xy is the mask or the filter. So how do you perform a convolution? In order to perform convolution on an image, the following steps should be taken. You flip the mask horizontally and vertically only once. You slide the mask onto the image, multiply the corresponding elements, and then add them. You repeat this procedure until all values of the image have been calculated. So here is a diagrammatical representation of this. We have our mask, and you can see at the top the numbers 1 through 9. If you flip the mask horizontally, you get the arrangement that you see in the middle, and then flipping the mask vertically, you get the arrangement that you see at the bottom. I encourage you to pause this here and look at this slide and think about the process of flipping horizontally and flipping vertically. So with convolution, this is an example of convolving mask over an image, and it's done this way. You place the center of the mask at each element of an image. You multiply the corresponding elements and then add them. Then paste the result onto the element of an image on which you place the center of the mask. The box in the red color is the mask, and the values in the orange are values of the mask. The black color box and values belong to the image. Now, for the first pixel of the image, the value will be calculated as follows. The first pixel is 5 times 2 plus the quantity 4 times 4 plus the quantity of 2 times 8 plus the quantity of 1 times 10, which is 10 plus 16 plus 16 plus 10 equals 52. So you would place 52 in the original image at the first index, and then you would repeat this procedure for each pixel of the image. This is the way the mathematical operation happens. With a convolution kernel or mask, convolutions are mathematical transformation of pixels, and it's carried out in a different manner, or in a manner that differs just from simple addition, multiplication, or division. You can see in figure 6 that this is a sharpening convolution kernel mask, And it's showing the original images with, you can see the red box. And then the resultant output is shown below that. And then finally, the destination image target pixel has a different value. So the results of this mask, that pixel that had an original value of 9 has a final value of 130. So the operation begins when the convolution kernel is overlaid on the original image in such a manner that the center pixel is matched with the single pixel location to be convolved from the input image. The pixel is referred to as the target pixel. Next, each pixel integer value, often termed the source, from the original image is multiplied by the corresponding value in the overlying mask. These products are summed, and the grayscale value of the target pixel in the destination image is replaced by the sum of all the products ending the operation. The convolution kernel is then translocated to the next pixel in the source image, which becomes the target pixel in the destination image until every pixel in the original image has been targeted by the kernel. I'm going to finish up here with an example of smoothing convolution filters, often called smoothing filters, and they're used for reducing random noise in digital images. A typical smoothing convolution filter is illustrated in figure 7 as shown here, and it's basically a matrix having an integer value of 1 for each row and column. This image is showing an example of smoothing kernel on the left, the original image in the right, in the center, and the sharpening kernel on the right. The 9 integers in each smoothing kernel add to a value of 1 when they're summed and divided by the number of values in the matrix. So these kernels are designed so that the convolution operation will produce an output image having an average brightness that is equal to that of the input images. This may only be approximate. So in general, the sum of terms in most convolution kernels will add to a value between 0 and 1 in order to avoid creating an output image having gray values that exceed the dynamic range of the digital to analog converter utilized to display the image. So smoothing convolution kernels act as low-pass filters to suppress the contribution of high spatial frequencies in the image. We use the term spatial frequency and as analogous to the concept of frequency with respect to time or temporal frequency, and it describes how rapidly a signal changes with respect to position in the image. And finally, a little bit about lookup tables. So a lookup table is produced during this process, which relates input to output values for the stretch. It's efficient since each possible value for output dn is computed only once. The image rescaling is done in virtual display memory and does not affect data on your disk. So you can see here we have our central processing unit, and then we have a video memory to the right, and a lookup table with the blue, green, and red, and then the final image. This example is showing a TV monitor, but it's the same for a computer monitor. This is an example of a lookup table. Again, just to show you what one looks like. No need to memorize something like this. Here's a graphical representation of a lookup table. And so the process here was to map input pixel values from 16 to 191 out to the full intensity range of 0 to 255. Input values of 191 or greater are set to 255, and input values between 16 and 191 are interpolated to the values from 0 to 255. And this is the resulting graph of the output intensity values. This concludes this lecture. Thank you.